Hi everybody, we're getting into section 5.2 today. Apologies, a couple of these pages are kind of blurry here, but hopefully you have your notes with you, so that shouldn't be too big of an issue. But we're going to start talking about the definite integral. So last time we were looking at the concept of area under the curve, right, and interpreting area as distance, approximating areas using rectangular approximations, right, using left-hand side, right-hand side, and midpoints in order to get approximate areas. Okay, so today we're going to start talking about more of the calculus terminology. So here in section 5.1 we saw that the area under the graph of a continuous function is given by the limit of this form. So here we have the limit as n approaches infinity, so that's the number of rectangles grows infinitely large, and then we add up, that's the sum, the height times width of each rectangle. So this is the area of each rectangle. Okay, so what we have here is the number of rectangles go to infinity. So we add, and then this is the area of each rectangle. So we add all those up, and there we go. This limit is called the definite integral of the function on the interval from a to b. Okay, so the definite integral is this limit, technically speaking. It's the limit that gives us that area under the curve, that exact area under the curve. Okay, so here again, apologies for the kind of blurry page, but suppose f is a function defined on the interval ab. Divide the interval into n subintervals of equal width. So here's our delta x definition here. So delta x is b minus a over n. And then we use the subdivision pointer x0, x1, all the way up to xn, etc. And then they talk about using a sample point, so kind of like using the midpoints. But it might be left endpoints, it might be right endpoints, could be the midpoints, could be any point that gets our approximation as close as possible to the actual area. And then we take the sum of all of those areas. Again, that's what this is here, the sum of all those areas. And then we add all of those up together. That's going to, as we take the limit, as n approaches infinity, right, get more and more rectangles, then we get what we call the definite integral. So the integral from a to b of the function. So that's this right here. Okay? And this is, of course, provided that that limit exists. If that limit doesn't exist, then this isn't going to work. But then we say that f is integrable on AB. When we say integrable, we just mean you're able to take an integral. Okay? So what does this notation tell us? Well, this symbol, so the integral symbol here, was introduced by Leibniz, one of the creators of calculus. The reason that we use this symbol is because it represents the letter S, and S is because we're talking about a limit of sums. Okay, so we're talking about sums, so we have an elongated letter S to describe the integral. So in this common notation here, some things to note. So f of x, that inside part, that's going to be the integrand. So the integrand is whatever function we are integrating. Okay, whatever function we're taking the integral of, or finding the area beneath, if you want to think about it that way. The numbers a and b, these are called the limits of integration. Okay, another word that you'll hear me use for them is they're also called the bounds. Okay, so that's kind of our shorthand talk, instead of saying limits of integration every time, but that just tells us we're going from what value to what value, so from the lower limit to the upper limit, okay, or lower bound to upper bound. Okay, and then our symbol dx next to the integrand there indicates that the independent variable is x. So dx kind of acts like a placeholder, telling us what variable we are using in this function, which will become really important when we get to higher levels of calculus, where you have a lot more variables being thrown around. Okay, so this is called integration, to compute an integral like this. Okay. So one important thing to note, the definite integral is a number, and I'll circle that again. it is a number and does not depend on x. In fact, we can use any other letter in place of x, so it really doesn't matter the letter inside. We use x, we use t, you can see a u in there as well. But the important thing here is the integral gives us a number, because remember the integral is area, right? It's area under a curve, and area is numerical. Okay? So express the following limit of Riemann sums as an integral on the interval from 0 to pi. So we're not solving anything, we're just converting here. So we have the limit, the number of rectangles goes to infinity. This function in here is going to become our integrand. Our delta x, that's going to turn into our dx. And our bounds come from the chosen interval. So this is going to be equal to the integral from 0 to pi, lower bound to upper bound, of x cubed plus x sine of x dx. So this would be our integral that represents the same thing as that limit of the Riemann sum. Okay, so there's our definite integral for this situation. Okay, now looking at interpretations in terms of area. So like I kind of been talking about, definite integral does give us area. In fact, it gives us exact area. So generally what we've been looking at so far has been, right, you get a rectangle, approximate area, approximate, 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 etc. all the way down the line. And then you get either an overestimate or an underestimate, but what we would really like to be able to do is just get that exact area under the curve. Okay? And in order to do this, at this point, right, we're just taking that limit of Riemann sums. If we have something a little more geometric in nature, like rectangles, triangles, we can work with those a little bit more easily. But we will be developing ways of computing this area in future sections. Okay. So whenever you have a positive function from a to b, so if we're above the x-axis, then the integral is going to give us the area under the graph of f between a and b. Okay, so this works when you have a positive function. So let's look at an example. Consider the integral from -2 to 0 of the square root of 4 minus x squared dx. Interpret the integral as an area and find its value. Okay, so before we even look at the integral, I just want to look at the integrand. I want to look at that function. Okay, let's graph it on the interval from -2 to 0. Okay, so from here to here. Alright, so let's just plug in a couple points. So plug in -2 into here. You're going to get 4 minus 4 is 0, square root of 0 is 0. So there's a point right there. And then plug in 0. You get 4 minus 0 is 4, square root of 4 is 2. So that's going to be right up here. And if you were to find other points in between, you would get a shape that looks kind of like, oops, let me round that a bit more. Something like that. Okay. Now, what is this shape? You might be able to tell by looking at that function there, but this is part of a circle, right? If I were to continue this onward, it would go like this, right? And it would look more circular than that, but it would give us a circle. Okay? So, what we're looking for here is this area, the area beneath this curve from 0 to 2. So this whole area down here. Alright, so in this case, this is going to be, so this is circle of radius 2. But this piece isn't the whole circle, it's actually just 1/4 of the circle, right? So we have 1/4 of the circle. So, to get the area, all we need to do is get 1/4 of the area of the circle. So our area A So that's our integral from -2 to 0 of the square root of 4 minus x squared dx. This is going to be 1/4 pi r squared, and the r, and this time the radius, is 2. So that's 1/4 times pi times 4. The 4's will cancel, and we're just left with pi. So the area of this quarter circle, right in here, this whole area here, from -2 to 0, is pi. And that is the exact area. Okay, that's not an approximation. That is exact. All right. Now, that was if the function is positive on the interval from a to b. So what if the function is negative? Well, if it's negative, then basically we're still computing area between the x-axis and the function. However, if it's below the x-axis, we count the area as negative. Okay? So, and the reason we're doing this is because if we were to draw rectangular approximations down here, right, even though they are taking up physical space down here, the value that we're using for the height is a negative number because it's down here somewhere. So we would end up getting a negative area. Okay, and that's okay. We are able to get negative areas when we're talking about integrals, an area under a curve. Okay, so the definite integral will give us a negative area if the curve is below the x-axis. Now, not every function is just described above the x-axis or below the x-axis. Sometimes we have a combination of both. So if we have any function in general that goes above or below the x-axis, if you want to find the value of the integral, the value of that area, you just take the areas above the x-axis and add them, and then you take the areas below the x-axis and you subtract them. Okay? So we compute the area the same way, and then we just take the positive ones and then subtract off the ones below. Alright, let's look at this example. So evaluate this integral by interpreting in terms of areas. So we have the integral from 0 to 3 of the function x minus 1. So x minus 1 we can graph. This is a line. So x minus 1, we have a y-intercept down here at -1, and then it goes up 1 over 1 all the way, and then we're going up until 3, it says. So we'll just stop there. Draw the line. Okay, let me thicken that up a little bit. So we have our line. Now we're looking for area between the curve and the x-axis. So we're going to split that into two pieces because we've got this area down here, which is below the x-axis, and this area up here, which is above the x-axis. Okay, so I'm just going to call these A1 and A2. Alright. So to compute these are just right triangles. So we can go ahead and just find the area geometrically. So A1, that's going to be 1/2 base times height. That's the area of the triangle. 1/2 the base from 0 to 1, so that's 1. Height is 0 to 1, that's 1. So the area of that triangle is just 1/2. A2, we have 1/2 base times height. The base from 1 to 3, that's 2. And then from 0 to 2, so that's going to be another 2. So the area up there is 2. So the value of the integral, the total area under the curve, so x minus 1 dx, that's going to be positive area minus negative area. So that's 2 minus 1/2, which is 1 1/2 or 3/2 as an improper fraction. Right. So that's the value that we get for the combined area, taking into account the positives and the negatives. Okay. So, according to the definition, definite integral is the limit of the Riemann sum, so we've talked about that. So we can approximate the definite integral by taking a Riemann sum. So if we're not able to take that limit, because these can get pretty complicated, we can still approximate the value of these integrals using a sample point. Generally, we like picking the midpoint because it is a little simpler to work with. So this kind of goes back to what we were doing last section, just being able to approximate the value of the integral. Okay, so when you're picking your midpoints, again, you can determine how wide your interval is going to be, and then you can get the middle of each of those intervals by just adding up the endpoints and dividing by 2. Right, just get an average. Okay, so let's look at an example. So the graph of the function f is given. Estimate the integral from 0 to 8 of f of x dx using 4 subintervals with right endpoints. Okay, so if we're using 4 intervals, then our delta x, that's going to be b minus a over n, 8 over 4, so that's 2. So we're going to go, 0, 2, 4, 6, and 8. Alright, and then we're going to get the midpoint of each of those. In this case, it's a little easier, right? Halfway between 0 and 2 is 1. So that's going to be right there. And that's going to allow us to draw our rectangle. Whoops. I'm sorry, we're doing right-hand endpoints now, aren't we? So ignore that. We'll get to the midpoints in just a second. Got a little bit ahead of myself. So right-hand endpoints. So that's going to be 2. So we draw that. At 4. Okay. At 6. So now at 6, it's going to go down. So it doesn't matter that some of the graph is above and some is below, because the right-hand endpoint is all we're looking at right now. And at 8, the right-hand endpoint is at 0. So actually, we're just going to have kind of a flat piece. So it's a rectangle with no height, right? 0 for its height. Okay. So if we're looking at these areas here, okay, so these areas here, and then nothing for that last one. So we can go ahead and approximate. So the integral 0 to 8 of f of x dx is approximately equal to, so we can just kind of guesstimate at the heights here because it doesn't give us an exact picture of what's going on, but it's going to be height times width. So the first rectangle looks like about 3.5 times the width is 2, plus height of the second one looks like about 1.5 times 2, plus negative 2.1 it looks like, times 2, and then plus 0 times 2. All right, no height on that last one. So that gives us 7 plus 3 minus 4.2 plus 0, of course. So that's going to be 5.8. So we get 5.8 for our approximation using the right-hand endpoints. So now, let's go look at doing the same thing with the midpoints. So for the midpoints, so again we have delta x is 8 minus 0 over 4, which is 2. So we go 0 to 2, 2 to 4, 4 to 6, 6 to 8. And now let's go ahead and get those midpoints. And then use those to determine the heights of the rectangles. And then at 3 here. And then right there. And then 7 is the midpoint of this last one. Okay. All right. So let's set up our integral. So we've got this area here, this one here, this little area down here, and this one here. Okay, so it looks a bit different, right? Not entirely different, but somewhat, because we've got a different sample point that we're choosing. So integral 0 to 8 of f of x dx is approximately, so let's go with these heights now. So I had that pegged as 3.1 approximately, plus that next one, oops, that next one looks like, if you look at the picture on your graph, I think I rounded this up a little bit. I think it should actually be 2.9, a little bit closer, times 2. But if you put 3, that's fine. It's all in the same ballpark. Plus that one, we're looking at about negative 0.5, it looks like, times 2, plus negative 2.5 times 2. So that's going to be 6.2 plus 5.8 minus 1 minus 5. So that gives us 11, 12 minus 6, which is 6 for our area, which is pretty close to what we got before at 5.8 versus 6. So it looks like we're in the same ballpark here with these values. Okay, and these are again just approximations. Okay, so let's start looking at some of the properties of the definite integral. So a lot of properties to talk about today. I'm just going to start running through these. So when we're talking about the bounds, so if you have an integral from a to b, if you want to reverse the order of the bounds, the integral from b to a, then you have to make the integral negative. Okay, so flipping the bounds negates the integral. Okay. If you have an integral going from a to b where a equals b, so in other words, it's going from, we generally write this like a to a, right? Think about that in terms of area. Well, if it's starting here, so here's our curve. If it's starting at a and ending at a, then there's no area here, right? That's not a rectangle, that's just a line segment. So the integral would be 0. Okay, so the integral from a number to itself is 0. Suppose f and g are continuous functions. Okay, if we take the integral of a constant, that's going to be equal to c times b minus a. The reason for that is because if we have a constant function, that's just a horizontal line at c. So the integral from a to b, that area, is just the area of this rectangle with a height of c and a length of b minus a. Okay, so the integral of a constant is just the constant times b minus a. If you have the integral of a sum, you can split it up across addition. So you can split it into 2 separate integrals. Similarly, let me jump ahead here, if you have subtraction, you can split that into 2 separate integrals as well. And if you have a constant times a function, you can pull the constant out of the integral. The reason that we're able to do all of these are because integrals are defined as limits, right? It's the limit of that Riemann sum. And limits allow us to do all of these things. So the rules of the limits also apply to these integrals as well, okay? Which makes it nice to work with because we already have kind of an idea that we should be able to do these things. So let's look at this example here. So an interesting example where we are given that the integral from 0 to 1 of x squared is 1/3, and use the properties of the integral to evaluate the integral from 0 to 1 of 4 plus 3x squared dx. Okay, so we're going to get a little creative here. All right. So let's start using these properties. I want to get the integral of just an x squared by itself. So to do that, we need to start splitting this up. So first thing I can do, I can split up across the addition, right? This becomes integral 0 to 1 of 4 dx plus integral 0 to 1 of 3x squared dx. And then pull out the constant in that second integral. So plus 3 times the integral 0 to 1 of x squared dx. And now start evaluating. The integral here, that's a constant, so that's just going to be 4 times b minus a, so 4 times 1 minus 0, plus 3 times this integral is given to us in the problem, right? That is 1/3. So just sub that in. So we get 4 plus 1, which is 5. So we were able to use that other integral to help solve this more complicated one. We got that the integral, the value, that area under the curve, is 5 for this function. Okay. Next property, if we have the integral from a to c of f of x dx, you can actually split that up across the interval. So the area under the curve from a to b plus the area under the curve from b to c is equal to the area all the way from a to c. Okay, so they kind of, let's see, looks like they labeled these wrong. So based on that formula, this would be b, and then this one would be c. Let me fix that. So this would be b, and that one would be c. Using, oops, and that would be b, and that would be c. If we're being consistent with this formula. Okay, typically we rewrite it the other way, where a and b are the bounds, but that's how they wrote it in that theorem, so we'll just keep it like that. So, but all this is basically saying is if you take the area of the whole thing, that is equal to the area of the first part plus the area of the second part. Okay, add those together and you get the entire area all the way. Okay. Let's look at this example. If the integral from 0 to 10 of f of x dx is 17, the integral from 0 to 8 is 12. Find the integral from 8 to 10. So this is just direct use of this property. So the integral from 0 to 10, from 0 to 10, we can split this area up. Instead of being 0 to 10, we take the piece from 0 to 8 and the piece from 8 to 10. And that gives us the whole interval again. So this is integral 0 to 8 f of x dx plus integral 8 to 10 of f of x dx. This one we know, and this one we know. So that's going to be 17 equals 12 plus the integral from 8 to 10. Okay, and then subtract. So integral 8 to 10 of f of x dx equals 17 minus 12, which is 5. Okay, so a nice, concise solution on that one, just directly using that property that we just talked about. Okay. Here are a few more properties. These are the comparison properties of the integral. So if we have the function is greater than or equal to 0, then the area under the curve, right, that's what the integral gives us, that integral must be greater than or equal to 0. Right? If the function's positive, the area under it has to be positive. If one function is bigger than the other on the interval, then the area under that one is going to be bigger than the area under the smaller one. Right? So if we have, for example, like here, here's F, here's G, here's A and B, right? All this is saying is the area under f, which is all of this, must be bigger than the area under g, which is this portion. That's what that property says. Okay? As long as one function is above another, the area beneath it must be greater. Okay? And then number 8, that last one there, if a function is bounded between two constants, so little m and big M we're calling them, then the area, that integral, must be between little m times b minus a and big M times b minus a. So how do we get these formulas? Well, this is the area of a rectangle, and this is the area of a rectangle. Okay? So if you look on the next page, it gives a more clear diagram. So right here. So you can see here's little m right here. Here's big M right here. So we're saying if the function f of x is between these two values everywhere from a to b, then the area under the curve, so this whole area under this curve, must be bigger than the area of this rectangle, but smaller than the area of this rectangle, which you can see is just the whole thing. Okay, so it's bigger than the area of the small rectangle, but smaller than the area of the big rectangle. Okay, so again, this is the area that we're looking at here. Okay, so let's use this property to estimate the integral from 0 to 1 of e to the negative x squared. So we can bound this, go ahead and create some boundaries here. Oops. Up here and down here. So we know that e to the 0 is 1. So we're just going to use big M is 1. Little m, I know e to the 1 is, or e, I should say, this is using e to the negative x squared, so that would be e to the negative 1, so that's 1 over e. So little m is going to be 1 over e. And the idea is the entire function is going to lie between those two rectangles. Right? The area is going to be between those two values. Okay, so we have the integral of from 0 to 1 of e to the negative x squared dx is bigger than 1 over e times, right, the width is 1 minus 0. Oops. And it's less than 1 times 1 minus 0. So this is just 1 over e less than or equal to integral, which is less than or equal to 1. And we can see from the diagram that clearly that's true. If you're curious, this value is approximately 0.368. Okay, so the value of that integral, that area under the curve, must be between about 0.368 and 1.